Hello, we're going to talk about redox titration. Your next to last lab of the year is to do a redox titration to determine whether a commercial hydrogen peroxide solution actually meets the label claim. Redox titration has some similarities and some differences with acid-base titration, which you've already done. First of all, how is it the same as an acid-base titration? Well, in any titration, you have both a titrant and an analyte. Well, now I don't know how to write on here. There we go. So we have a titrant. And just like always, our titrant, we know the concentration, which we're going to know in terms of molarity. And we have an analyte, whose concentration we don't know. And just like in acid-base titration, the objective is to determine the concentration of our unknown analyte. In this case, that would be the hydrogen peroxide solution. Oops, I don't know how to get rid of that, so you're just going to have to ignore it. Differences between acid-base titration and redox titration are that in acid-base titration, we're dealing with proton transfer, or hydrogen, H+, where the acid transfers a hydrogen cation to the base. In redox titration, there's no hydrogen transfer. Instead, there's electron transfer. As we've talked about, with redox, one of the species gains electrons, one of the species loses electrons, and when that electron transfer happens, that is what defines a redox reaction. With the acid-base titration, we have to include an indicator because the acid and the base themselves don't have a difference in color. So the indicator is used to give us a visual indication of when the titration is over. With redox titration, oh, hold on. Let's write that down. Indicator. With redox titration, the analyte and or the titrant themselves have color, and so when one of them is used up or when one of them reacts and goes away, there's a natural color change that automatically happens. So with electron transfer, we have no indicator, and with redox titration, we have no indicator. Rather, we have a natural color change that signifies the endpoint of the reaction. And so there's no difference between endpoint versus equivalence point. In this case, they're the same, so we don't have to worry about a difference there. Yay. So in part one, there's two parts of this redox titration. In part one, you are going to standardize your concentration of the permanganate solution. Ultimately, you're going to be using this permanganate solution to determine the concentration of the hydrogen peroxide. But as you read in the pre-lab handout, the permanganate solution is subject to a lot of contamination by other ions, by other salts. And so you think you've made a whatever concentration of permanganate, you probably really haven't. So we're going to use the permanganate, the MnO4-, as our analyte, and use the Fe+2 concentration as our titrant. So the Fe+2 concentration you're going to be able to calculate, or not to calculate, but to measure and determine very, very precisely. And handwriting, my goodness. Okay, bear with me. That precise measurement that you're going to use to make that Fe+2 titrant, you're going to use the analytical balance. You're going to use your volumetric flasks. You're going to use any and every method that you can to make sure that that molarity is known really, really, really precisely. And so you're going to standardize that MnO4, which means you're going to use a known concentration of iron 2 cation to titrate and calculate the exact, precise, accurate concentration of your permanganate. Secondly, you're going to use your permanganate I'm not used to the stylus, can you tell? To titrate with your H2O2 solution. Part of the pre-lab assignment is to figure out what volume of this you're going to need to use, and I will tell you it's a lot less than you think. So you're going to write the redox reaction to balance between those. You're going to balance it. You're going to figure out approximately, if you intend to use, say, 10, 12 or so milliliters of permanganate solution, what volume of hydrogen peroxide do you need to put into your flask in order to titrate it? The ultimate goal of this is to determine what is the actual percent of your hydrogen peroxide solution, and is it 3% as the hydrogen peroxide label claims. You've titrated before. You are an expert at titrating, and this titration is no different from any titration you've already done. First of all, you're going to rinse your burette, which is the long, tall thing on the ring stand with the clamp. Okay, there's a very technical looking clamp. You're going to close the stopcock. You're going to rinse, put some of your titrant in. You're going to swirl it around, rinse out any impurities, drain it out, and clean your burette with the titrant before you fill it. So you're going to drain it, and then you're going to fill. You're going to notice a slow progression toward the color change as you get near the end point, which is also the same as the equivalence point in this case. As with any titration, your objective is that the last drop of titrant added should cause the color change and that you haven't added any unnecessary drops. If you do that, you have done it wrong, and you're going to have to go back and redo that trial. So you're going to slow down near the end point, you're going to add it drop-wise, you're going to make sure you're swirling really well, just like any other titration. So this is a hard lab, not necessarily in terms of the hands-on aspect of it, but in the planning and execution of it. So first of all, you're going to be making your own solutions of permanganate and of the iron +2 solution. And I've never asked you to do that before. So you're going to be using glassware that is highly precise. You're going to be using the volumetric flask, which is the thing in your drawer that looks vaguely like this. It's got a marking here. Okay, like that-ish. What you're going to do is you're going to weigh out your solid that you intend to use very precisely on the analytical balance. You're going to put it in, and you're going to fill this up with water up to the marking. You want, at that point, here's a close-up of that. So here's the marking. You want the bottom of the meniscus to be level with the marking, and that makes the volumetric flask contain the exact amount that it purports to contain when you look at the label. The next thing that makes this difficult is that you are making your own solutions, and your own solutions are your own. So if you make an error and you need to redo it once or twice or 3 or 4 times, you are working with your own limited resources. So if you run out of permanganate solution, you're kind of in a world of hurt, because everyone else's permanganate solution is not the same concentration as yours. So you don't have the freedom to make errors over and over and over again. Not that you would, because you're a competent individual, but you should definitely make sure you know what you were doing the first time, or at least the second time, knowing that the resources you have are limited. Now, I have in the past had students who have said, I believe that I'm probably going to make an error. I'm going to make extra solution just to hedge my bet a little bit. You're welcome to do that, but all of the solution that you make needs to be made in one batch so that all the concentrations of it, all the volumes of it that you intend to use have the same concentration. All of the reactions in this lab are done in acidic medium. If you forget to acidify the MnO4 minus and the H2O2 reaction, if you do not add the H plus in the form of H2SO4, your reaction will turn a weird color. It won't really work. The acid catalyst there is really, really important to make the reaction go. And if you forget to acidify it, essentially you'll waste a trial, and the reaction won't happen, and it will be disappointing. Lastly, we have not done a lot of work with percentages. of reagents. So you're dealing with H2O2, which is hydrogen peroxide, and the label claim is that it's 3%. That essentially means you have 3 grams of H2O2 over 100 grams of solution total. Well, that's hard to convert into a molarity, but not really. So 100 grams total, if we assume that that is mostly water, that's approximately equivalent to 100 milliliters. The 3 grams of H2O2 you can convert into moles. And so what you can do is turn your grams of H2O2 into moles of H2O2. H2O2. You can turn your grams of total solution into an approximation of milliliters and convert that to liters. And then you've got moles per liter. That's a molarity, and that's something that you're used to working with. So why am I making you do all of this? There's some educational goals and there's some practical goals. Making your own solutions is very educationally valuable. We've been working all year with molarity values and solutions that I have simply handed you and said, hey, students, this is 1.00 molar or whatever it is. In this case, you are making your own solutions. You get to see the ins and outs of that happening. So that's a valuable skill to have as an intelligent citizen of the world. So that's number one. Number two is that you need manual practice with titration. With the burette and using the burette and meeting the endpoint without overshooting it. You're going to go to college, and I want you to be proud of your titration skills. Thirdly, this is, you're basically practicing an analytical technique. There are people in the world who substantiate the label claims of things like H2O2, where they look at the H2O2 bottle, they titrate that to see if it actually is 3% higher or lower than 3%, because consumers have a certain expectation of the product that they're buying. The Consumer Product Safety Commission has a stake in whether label claims are accurate or not. One or more of you may grow up to be an actual real-life analytical chemist, and you may use this technique professionally. So it's just nice to see a situation where a technique that a high school student could do easily in the lab, which is titration, could be used professionally to accomplish something like testing a label claim. I think it also would be just kind of interesting to see whether the generic versus the name brand, or the old versus the new H2O2, whether there's really a difference. And that will be something that our class can talk about once people gather results for their own individual samples. So thank you for watching. I hope you learned some things about your redox titration. You have a worksheet to do, and you have a whole lab handout that will help you understand. Good luck, and you can come find me if you have questions. I don't know how to turn this off.